Okay, our next speaker and final speaker of the day is Claude LeBrun. He'll be speaking on twistors, quasi-Fuchsian three-manifolds, and almost-Kaehler geometry.
Well, thank you, Matt. Thanks to the organizers. It's a real pleasure to be here among so many old friends, and I hope by the end of the week among many new friends. I'm going to begin by telling you a rather old story, but one which I've discovered is not necessarily well understood by some of the young people who are interested in it. So let me begin by talking about mini twistors in hyperbolic three-space. So a good way to think about hyperbolic three-space is that you can think of it as the unit ball in R3 with a metric which is a conformal rescaling of the Euclidean metric. And for this metric, the geodesics are Euclidean circles or segments of circles that are perpendicular to the boundary sphere. And in this picture, of course, it's a conformal, the metric is a conformal rescaling of the Euclidean metric, so in fact, angles are the same as they would be in Euclidean space. So there is a beautiful mini twistor space associated with hyperbolic three space. It's from a real point of view, it's the space of oriented geodesics in R3, in H3 in hyperbolic three space. So if you're trying to parameterize an oriented geodesic, it's enough to know its initial point and its final point at infinity, and those uniquely determine the geodesic. So that means that as a point set, you could think of the oriented geodesics in hyperbolic three space as being parameterized by the product of the boundary sphere with itself minus the diagonal. But in terms of the orientation I'd like to give it, the first factor, I'm going to give the reverse orientation. So the overbar has changed the orientation to give it the inward pointing orientation rather than the outward pointing orientation as the boundary of the three ball. Okay, so so this is set up so that for a geodesic, you want the in-pointing orientation at the initial point so that it's consistently oriented with the final outward pointing orientation at the final point. If you do it that way, then there is a very simple and natural complex structure on the space, which corresponds to the fact that given a Jacobi field along a geodesic perpendicular to the geodesic, so that would be, I've drawn this actually as if it's in Euclidean space, but on a very small scale, of course, hyperbolic space looks like Euclidean space, so the picture is not too much of a lie. So given a connecting vector field that points from one geodesic to another, you can rotate it by 90 degrees relative to the orientation. And because the curvature is constant, that takes a Jacobi field to a Jacobi field. Now, that means that the space of geodesics actually, you could worry maybe this is not an integrable almost complex structure, but it is in fact integrable. And it's simply thinking of the initial and final positions as points in CP1. So here, so if you orient it so that this is the Riemann sphere times the Riemann sphere, the thing that you initially thought of as the diagonal becomes, if you like, the anti-diagonal, because to do it this way, I have to choose some orientation reversing map. This is an anti-holomorphic map on CP1 that just given by conjugation of the two coordinates is the simplest choice. And then the anti-diagonal is the graph of that of that orientation reversing map, and it's exactly the fixed point set of an anti-holomorphic involution, which interchanges the two variables and complex conjugates them. All right, so the mini-twistor correspondence says that you can think of a point in hyperbolic 3 space as corresponding to a holomorphic curve in this mini-twistor space. So it's a copy of CP1, which in CP1 times CP1 that misses this anti-diagonal. And so here I've drawn the anti-diagonal as this dotted line, and the curve we're talking about might be the usual diagonal. So it's something that's, as in the homology class of this CP1, it's actually in the same homology class as the diagonal. And there's a family of such things, actually, when two of them, so that you have families through a pair of points corresponding to different points on a geodesic. And the last, so right now this would be a larger family if I didn't also require that the curve we're looking at is invariant under this complex conjugation I talked about. So there's this interchange of factors and complex conjugation. So when you, so the mini-twistor lines form a family, actually in one-to-one correspondence with the three-dimensional ball or the hyperbolic 3 space. Another picture, you might think of the CP1 times CP1 we're thinking of as a quadric in CP3, smooth quadric, and then the kinds of curves that one gets are all plane sections, and the fact that a plane section depends on in this dimension really essentially depends on 3 parameters is consistent with the rest of the picture. Okay, so so that allows one a certain holomorphic way of thinking about certain questions about three-dimensional hyperbolic geometry. So these curves are called mini-twistor lines, and the point is that every point in the hyperbolic 3 space corresponds to such a curve. Namely, you can, given a point in a hyperbolic 3 space, you can look at all of the oriented geodesics that go through it. There's a 2-sphere of such things. And so for each point in hyperbolic 3 space, we get a mini-twistor line. They all satisfy these properties, but in fact, they are the only holomorphic curves with these properties. I think this example was first discussed without emphasis on the complex conjugation aspect or the real aspect by Nigel Hitchen, but Nigel Hitchen, not much later on, also described the corresponding geometry of Euclidean 3 space in great detail and used it to study the Bogomolny equations. Paul Todd and Philip Jones also, by the mid-80s, had written a very nice exposition, including this example, but also including others, of these so-called mini-twistor correspondences. So the thing that I want to explain is sometimes called the hyperbolic ansatz, and the main point is that if you have a suitable positive harmonic function on a region in hyperbolic 3 space, you can associate to it an anti-self-dual 4 manifold. In other words, you can get an oriented Riemannian 4 manifold for which half of the Weil conformal curvature tensor vanishes. So the surviving part is W minus. That's why they're called anti-self-dual, but the equation is actually W plus equals 0. So the way this works is, for simplicity, let's just start with a convex open set in hyperbolic 3 space, and then it determines a corresponding region in the mini-twistor space CP1 times CP1 which would be all of the oriented geodesics that meet it. All right, so there is a neighborhood of a reference mini-twistor line corresponding to some point in it, but there's a tubular neighborhood of that, which consists of geodesics that meet the given convex set. Okay, so the interesting point is that there is a very nice reinterpretation of harmonic functions on this convex set in terms of the mini-twistor space. There's a Penrose transform which says that for simplicity right now, let's say complex valued harmonic functions on that region are represented by elements of the first cohomology of U hat, the region in mini-twistor space, with respect to the holomorphic function. So it's H01 of the region in hyperbolic space. Now, on the other hand, there's the usual exponential sequence that the first cohomology lives in. So this is a simply connected region of the way I've set it up, it's automatically a simply connected region of CP1 times CP1. And so, in fact, you could think of H1 of U hat O as just H1, the elements of H1 U hat O times, the non-zero holomorphic functions, where this is multiplication, and where this actually just means the holomorphic line bundles on U hat, which have the extra property that the first Chern class vanishes. So there's a correspondence between harmonic functions on a convex region of hyperbolic space and the holomorphic line bundles on a corresponding region in the mini-twistor space. So the extra condition that these holomorphic line bundles satisfy is that their first Chern class vanishes. That's, in fact, the mini-twistor lines contained in this subset are actually deformation retractions of it. So the condition is the same as saying that the first Chern class vanishes on one of those CP1s, but that's true if and only if on the CP1 the line bundle you're talking about is holomorphically trivial. Now, this puts us in the realm where, so I've said right now that there's a version of the Penrose transform which would give you this translation of harmonic functions into cohomology classes and then into holomorphic line bundles. But a more geometrical way of understanding what's going on is to think of these harmonic functions as actually determining solutions of the U1 Bogomolny equations. So the U1 Bogomolny equations would say you have a complex line bundle with a connection on it, where the curvature of that line bundle is the Hodge star of some function, where the function is called the Higgs field in this context. But it's sort of an elementary fact that if you have a harmonic function, one way of understanding what is the Laplacian is to say you take D star D. Minus star applied to that if you like. So the star operator turns every harmonic function into a closed two form. And if you're on a region which is just contractible, of course, you could write that as D of a one form. A more sophisticated way of, though, is saying you're taking the trivial circle bundle, and it is equipped with a connection one form, which happens to be, the vertical dt plus the pullback of some one form on your region U. So this is this actually can be directly deduced from Ward's twisted photon construction, because these are these Bogomolny equations hyperbolic 3-space are actually a dimensional reduction of the standard Maxwell equations in Euclidean R4 with respect to a suitable symmetry. All right, so so on each of these many twistor lines, the line bundle we're talking about is actually holomorphically trivial. So choose a trivialization that gives you a family. Actually, the standard trivialization would give you a particular lift of that holomorphic curve, and of course, there's a C-cross action on the non-zero elements, so you actually should think of getting actually a C-cross family, or C minus the origin family of this mini twistor curve. What's the normal bundle of such a curve? Well, if we actually put in, so I said before, I haven't used it now, I'm going to look at harmonic functions which are actually real and positive. So if you look at the normal bundle of such a lift of the curve, then the C star action gives you a trivialization of the vertical piece of the normal bundle, and the quotient is the pullback of the normal bundle on the bottom. And just for Chern class reasons, the normal bundle of the original mini twistor line in CP1 times CP1 is actually the O of 2 line bundle as Chern class 2. All right, so we have an extension of O2 by O1. However, there's a little bit more you could say about the normal bundle downstairs. These curves are actually transverse to both factors. That means you can think of the normal bundle as just the things that are tangent, let's say, to the first factor, but you can also think of it as the stuff that's tangent to the second factor. What's lurking there is there's actually a natural isomorphism between the tangent bundle of the curve. Think of that as isomorphic to the first factor tangent bundle. And then, on the other hand, that's isomorphic to the normal bundle. So the normal bundle is the tangent bundle in a kind of canonical way for these curves. So this extension is actually it's an extension of the tangent bundle by the trivial line bundle. So the extension class lives in H1 with homomorphisms from there to there. That's exactly the holomorphic one forms on the curve C. And that's actually just by integration, or if you like Serre duality, this is canonically isomorphic to C. So you get a number out, and this is one literal way of saying that given such a line bundle on the mini twistor space, there's a function that it determines, and that's actually the harmonic function. So this is actually a concrete way of inverting the Penrose transform, in one direction of the Penrose transform. So because we've assumed that our harmonic function is everywhere non-zero, that means in particular that this extension class is always non-trivial. And there's actually only one non-trivial extension of O2 by O, and that's O1 plus O1, up to bundle isomorphism. The splitting type is O1 plus O1. So you get, when you take the total space of this line bundle of the principal holomorphic line bundle over a region in CP1 times CP1, that is a complex threefold that contains a family of embedded CP1s of normal bundle O1 plus O1. And as Roger Penrose taught us in the 1970s, that amount of information allows you to create an anti-self dual manifold. With the reality constraints that I've imposed, I'm thinking of V as actually real and positive. The anti-self dual manifold will be created in this way as actually of Riemannian signature. So if you have a non-zero harmonic function on a region in a mini twistor space, you can think of the corresponding principal holomorphic line bundle as a twistor space. And if this function is actually real, and you might just by changing the sign, assume it's positive, then it actually will give rise to a Riemannian solution of the anti-self-duality equations. So the prototypical example of this is, suppose we looked at the function which is identically 1 on the entire mini-twistor space, and say, what does that correspond to as a line bundle on the full mini-twistor space? Actually, the mini-twistor space is a priori a little bit smaller than CP1 times CP1. You're supposed to throw out the anti-diagonal. It happens, though, this line bundle extends. Namely, on CP1 times CP1, you can pull back the O of 1 line bundle, the Chern class 1 line bundle. You can pull back the Chern class minus 1 line bundle from the other factor and tensor them together, and that would be the so-called O1 comma minus 1 line bundle over CP1 times CP1. So these, you could, concretely, a local holomorphic section here is a function which is of homogeneity, 1 in the first variables and of minus 1 in the second variables. But if you're just thinking about it on the level of line bundles, it's the Chern class 1 line bundle on one factor, tensor the Chern class minus 1 line bundle on the other factor. If you take the complement of the 0 section in this, this line bundle, so you're thinking of the principal holomorphic line bundle, then that can actually be identified concretely with CP3 minus a pair of skew lines. So in terms of homogeneous coordinates, the point is that O1 minus 1 actually acts on, so if you think of there being a projection from CP3 minus 2 skew lines to CP1 times CP1, where the projection is, the lines you're throwing out would be where these are both 0, or where those are both 0. That's a pair of lines you're throwing out. And then the projection is just regroup them and think of the first two as a point in CP1, the second pair is a point in CP1. And then if you naively try to group together these coordinates and those coordinates where they're just homogeneous coordinates on CP1 and CP1, the problem is that homogeneities are independent. But if you have something that's of homogeneity 1 in one factor and minus 1 in the other factor, you multiply the last two gadgets by that number, you get something which actually has, which rescales as it should to define an element of CP3. So this is something you can actually see in Euclidean 3 space. You're throwing a pair of skew lines out of 3 space. Any point that's not on those lines is joined by a unique line that meets the first and the second line. And of course, the proof is that the point and the second line determine a plane. The point and the first line determine a plane, and the intersection of those two planes is a line. Okay, so if you the point is that this is the holomorphic line bundle that corresponds to the function 1, and what that's saying is that the anti-self-dual manifold you're going to cook up here is conformally flat. CP3 is the twistor space of a conformally flat 4 manifold, kind of the universal object. Here we've just thrown out, for example, a couple of twistor lines. So the geometry of this manifold is it's actually, if you take hyperbolic 3 space times S1, the Riemannian product, of course, either factor is conformally flat, but that doesn't say anything about their Cartesian product. It's not true that the Cartesian product of a general conformally flat manifold times another one would be conformally flat. But this particular one, H3 times S1, is conformally flat. And so if you give take the hyperbolic metric on H3 and add on dt squared, where t is a local coordinate, standard local coordinate on S1, then what you get is a manifold which is actually globally conformal to the 4 sphere minus an equatorial 2 sphere. So the geometry of this is interesting because if you take, you think of hyperbolic 3 space as the unit future pointing vectors in Minkowski 4 space. And if you think of S2 as the unit, think of S1 as the unit circle in R2, then their product actually is then naturally embedded in Minkowski 6 space. But the observation is that just by looking at adding the norm squared, this is actually, every element in it is a null vector. It's actually sitting in the null cone. So if we start off with, we take the unit future hyperboloid in Minkowski 4 space times the unit vectors, the circle in R2, then and then look at the product that naturally sits inside the null cone. And there's a map to the sphere. You can think of the sphere as parameterizing the generators of this null cone. And the amazing general fact is that a simply connected Riemannian manifold is conformally flat if and only if it can be isometrically immersed into the null cone of the origin in Minkowski space. The point is that the metric here is just up to a factor. It's just the pull that the metric here is 0 in one direction. What happens as you go out these generators is just rescales the metric on the force here. Okay, so so this hyperbolic ansatz I said before takes harmonic functions on regions of hyperbolic 3 space and produces anti-self dual 4 manifolds. They might not be complete or anything, but here's a very concrete way of describing how this goes. If you have a region, I'll no longer assume that it's convex. If you have a region open set in hyperbolic 3 space, and you the fact that it's harmonic is the same as saying that the 2 form star dv is a closed 2 form on U. And now we're going to sneak in an extra hypothesis. That means that it has a de Rham class. It represents something in H2, and that would be in H2 with R coefficients, if you like. Let's assume by fiat that if our U is topologically complicated so that it has non-zero second Benning number, assume that this is actually an integer de Rham class. So if you like, that its integral on any closed surface is an integer. Then the Chern-Weil theorem says that if you have on a manifold, if you have a de Rham class in H2, which is actually an integer class, then it is in fact the first Chern class of a U1 bundle. Here this would be its image in real cohomology, modulo torsion. So there would be a principal U1 bundle which had a connection with that given curvature. So here we're starting with a positive harmonic function on some region of hyperbolic 3 space. We assume this quantization condition, and then you can say there's an associated U1 principal bundle or circle bundle on our region. So locally, when I say, so this is a principal connection. So in terms of local trivialization, if T is the fiber coordinates, this is something that locally would look like dt plus theta for a one form on the base on the region in hyperbolic 3 space. So now, and this is very nicely explained in the paper by Jones and Todd, for example. You could cook up an anti-self-dual metric which has a Riemannian submersion on the hyperbolic 3 space by multiplying the connection form by the inverse square of this positive harmonic function, and then just adding on the pullback of the hyperbolic metric on H3. Now, anti-self-duality is conformally invariant conditions, so a more convenient way to write this is often to multiply it by V and say that V times the hyperbolic metric plus V inverse times the square of the connection form will if V is harmonic and the connection form has curvature that's star dV, then this will automatically be anti-self-dual. And that's conformally invariant, so we could also multiply that by any non-zero function u we like. So u squared times this would automatically be an anti-self-dual metric. So let's see that this actually, So this turns out to give rise to lots of very interesting concrete anti-self-dual form manifolds you can write down in closed form. Some of those are actually things that come with scalar flat Kaehler metrics. So if you have a Kaehler metric in real dimension 4, then if it's zero, then a Kaehler metric in real dimension 4 is, with respect to the complex orientation, anti-self-dual if and only if its scalar curvature is identically 0. On the other hand, not every anti-self-dual metric arises as a conformal class of a scalar flat Kaehler metric. The extra criterion that you need is related to a certain line bundle having appropriate sections. So here we have our twistor space is a principal line bundle over a region in CP1 times CP1, but CP1 times CP1 has lots of sections of the O11 holomorphic line bundle. And so there's a four-dimensional space, if you like C2 tensor C2, of holomorphic sections of this bundle. But that bundle is actually the square root of the anti-canonical line bundle. It is the canonical line bundle of this complex surface raised to the power of -1/2. So when you pull this back to the total space of a principal line bundle, which has vertically, its tangent bundle is already trivialized, you end up with many different holomorphic sections of k to the -1/2, and it means that that the metrics you write down in this way are they have the Penrose transform for having a section of k to the -1/2 is saying that you have a solution of this equation. It's this is a solution of the 2-index twistor equation. So the cute fact is that this is a sufficiently overdetermined system that on a region where omega is not, if omega is real and it's non-zero, you can actually choose a conformal scaling of the metric so it has constant length. When you do that, it turns out that this is parallel, and it ends up making the metric. This is nicely explained in a paper written by my student Max Pontecorvo in '92, published in '92. So that says that at least locally, the metrics you write down out of this hyperbolic ansatz are actually, they can be represented by scalar flat Kaehler metrics, and not in a unique way. You get an entire different family of different complex structures for which these metrics are conformal to scalar flat Kaehler. Now, this sounds like the hyper-Kaehler story, where you have many different complex structures associated with a fixed metric, but this is a little bit different, because actually what's happening in this construction is that you get a family of complex structures compatible with a given conformal metric, and for each of those complex structures there is a corresponding conformal rescaling of the metric such that it becomes scalar flat Kaehler. So it's a little bit analogous to the hyper-Kaehler story, but it's actually different. As you change complex structure, you also have to conformally rescale the metric. All right, so the application of this that really got me excited, and one of the best papers I ever wrote was in 1991, appeared in Journal of Differential Geometry, is you can take k data points in hyperbolic 3 space, and you can associate to those points a certain positive harmonic function that's defined on the complement of these punctures, namely 1 plus the sum of the Green's functions of those points, where the Green's functions are specifically normalized so that they go like 1 over 2 to the radius at small radius. So here's an explicit formula for each Green's function in terms of the hyperbolic distance from that center. All right, so you now go through this. Procedure. The point is that if you look at star of dV for the potential I've just written down, around each of these punctures you have a two-sphere that generates the homology in dimension 2 of this punctured ball is generated by small balls or small spheres around these points. And the integral of star dV on each of those spheres is actually minus 2 pi. So the condition that 1 over 2 pi times the curvature is an integer class is fulfilled. So there is such a circle bundle, and one could write down this metric, V times the hyperbolic metric plus V inverse times the connection form squared. But you could also choose an interesting conformal factor. The one I've written down has the property that actually, first of all, the Riemannian completion of this manifold will consist of adding 1 extra point for each puncture and putting in an extra two-sphere corresponding to the two-sphere infinity. When you do that, it becomes a smooth compact form manifold. And in fact, with this conformal factor, it turns out that the scalar curvature is everywhere non-negative. It's kind of it has the zeros. With this particular metric, the scalar curvature vanishes at a finite number of points corresponding to punctures. But in particular, that means the Yamabe constant of its conformal class is positive. So what that ends up showing is that you have a lot of completely explicit positive scalar curvature or positive Yamabe constant conformal classes on any connected sum of CP2 bars that arise by this construction. So here, when I say CP2 bar, I just mean take CP2, that's an oriented four manifold, consider its the orientation reverse, and when I say connected sum, that's the procedure that you're familiar with where you can build up a genus 2 surface from 2 tori, you throw a standard ball out of each one and then glue them together in the boundary. Now, it turns out that this actually gives all possible homeotypes. Up to homeomorphism, these are the only possible positive scalar curvature simply connected compact anti-self-dual four manifolds. It's still not known whether these exhaust all of the diffeotypes. It's not even known whether a connected sum like this has exotic differentiable structures. One could show that it up through about, I guess, k equals 5, it's known that these are the only diffeotypes with these properties, simply connected, compact, anti-self-dual. But for k large, we have no idea how to prove this up to get the diffeomorphism statement, right? The best statement you can get is homeomorphism type. All right, so I mentioned that one also gets scalar flat Kähler metrics out of this. For example, what you could do is out of the same construction, you get a lot of asymptotic Euclidean metrics. So you could choose a particular point at infinity of hyperbolic 3 space, and then it becomes actually more convenient to think in the upper half space model of H3. So we have a potential that we wrote down before, and the conformal factor I now want to put in is z squared, where z is the vertical Euclidean coordinate that defines the zero set is the boundary plane. Okay, so in fact the metric has this very, very concrete form. It's v times the Euclidean three-dimensional metric plus z squared times v inverse times connection form squared. And that actually is a completely concrete, complete scalar flat Kaler metric after you do the completion in one simple, you still have to put in one point for each of these punctures, and you have to also put in a copy of the boundary plane. Now, so these points, if you think about, you're thinking about these in the upper half space, they project to points in, we're going to think of this horizontal plane as the complex numbers. So they pick out some complex numbers, and that actually will become the Z1 axis in C2. You've chosen k arbitrary points on the Z1 axis, and this actually turns out to be a metric with a circle symmetry rotating around the it's a rotationally invariant scalar flat Kaler metric in C2. Of course, but the metric is on the blow up of C2 at these centers, where the blow up is the standard procedure where you replace a point with the set of with the CP1 of all the complex directions through that point. There's one other little piece of data that comes from the construction. We had altitudes associated with these points, and those are actually turn out to the heights of these centers actually coincide up to a factor of 2 pi with the areas of the exceptional divisors you put in at those blow-ups. So the twistor spaces of these are also completely explicit. If you take the local idea was that the twistor space was basically a principal line bundle over a region in CP1 times CP1, but the global story is more complicated. The twistor space has a C-cross action, and the point is there's an open-end set in this twistor space of the form x times y equals a product of P1 up through Pk in the line bundle O1k minus 1 plus OK minus 1, 1, where the product would be an OKK. And so each of those terms here is actually just a section of O11 representing a point. It vanishes at a mini twistor line. So you take the product of the k mini twistor lines of those points, and then that gives you a very concrete model. Now the point is that if you're away from the vanishing of P1 up to Pk, so if you're off the union of those many twistor lines P1 to Pk, this really does have a structure like a principal C-cross bundle, because you can just scale up the first the x by t and the y by t inverse, and that's a free C-cross action, but it actually goes bad when you're looking at places where P1 through Pk vanishes, right? So there, you have in the subset where y is equal to 0, the subset where x is equal to 0, and also you just have the 0 element. So there are, rather than having a point having inverse image a single copy of C-cross, you actually inverse image consists of a couple of copies of C-cross and a point. All right, so I should say that what I've been describing is not exactly the twistor space. It is a bimeromorphic model. These are completely analogous to Hitchin's twistor spaces for the Gibbons-Hawking gravitational instantons of type AK. The cute point is the twistor spaces are actually bimeromorphic to algebraic varieties, and there are very few compact anti-self-dual properties with that property. The twistor space, it's not actually an algebraic variety, but it is up to bimeromorphic maps. So Noboru Honda has found some also very, very interesting examples with that property that are different. They're topologically of the same type, but they are geometrically different. All right, so what the question now is, this method, is it any good for producing compact scalar flat Kaehler metrics? Scalar flat Kaehler manifolds. I just showed you it could produce a lot of complete ones, and there are other variations on this where you can get other complete ones. What about you want to get a compact four manifold with a zero scalar curvature Kaehler metric? So if you have a compact Kaehler surface, then it's anti-self-dual if and only if the scalar curvature is identically zero. That's just an extension of something I said before. But if you then say, what does the Enriquez-Cadira classification tell you about the complex surface, there are basically two types of possibilities. It could actually be Ricci flat. So then it would be Calabi-Yau. The simply connected example would be K3, or it could be a torus, or it could be a finite quotient of those. Or the other possibility is it could be a ruled complex surface. So it would be bimeromorphic to something which is a CP1 bundle over a complex curve. So this second possibility definitely was known to exist because you could take the Riemannian product of a Riemann surface of genus 2 or greater and a two-sphere, or CP1, and endow the product with the product metric where you give one factor constant curvature +1 and the other factor constant curvature -1. And you may not know this, but when you take a Riemannian product of two manifolds, their scalar curvatures add. The fact that this has scalar curvature +2 and this has scalar curvature -2 means that the scalar curvature of the product is 0. So this is a scalar flat Kaehler manifold, but actually that's true for both orientations. So actually you would say, gosh, that means that both W plus and W minus vanish. This must actually be locally conformally flat. Actually, if you look at the universal cover is hyperbolic 2 space times the 2 sphere, and the same argument I showed you a moment ago is that that's a conformally flat manifold. So if now you're taking Minkowski 3 space times Euclidean 3 space, and you take the unit sphere and you take the unit hyperboloid, and the product would then sit in the null cone, and central projection gives you a conformal map to the 4 sphere. All right, so these are so-called minimal. These examples are minimal. That is to say, they do not contain. They're not the blow-up of another complex surface. What are there things that are actually non-minimal complex surfaces which admit scalar flat Kaehler metrics? And here, this hyperbolic ansatz comes to the rescue and gives one a lot of interesting examples. So you might remember. So the construction depends on the use of so-called Fuchsian groups. It's a very simple construction. I mean, uniformization says you can think of a surface of genus G as a certain quotient of the hyperbolic plane. So for example, in the genus 2 case, you can take a suitable regular octagon and make these identifications, and you've arranged that all of the internal angles are all pi over 4. And so, then that will, it's supposed to be pi over 2. And then it'll turn out that if you glue together with those rules, you get a very nice so this is a very concrete way of showing that on a genus 2 surface you have constant curvature metrics. So that's to say this puts the fundamental group into the isometry group of the hyperbolic plane. But on the other hand, the isometry group of the hyperbolic plane naturally sits inside the isometry group of hyperbolic 3 space. So we could think of that previous picture as actually being in a totally geodesic slice of hyperbolic 3 space, and there's a natural extension of the group action to hyperbolic 3 space. by the way, this equatorial circle is very special. It's called the limit set. Point on the is on the limit set if take some interior point in hyperbolic space, take its orbit, and look at the closure points of the orbit, and those can't be inside hyperbolic 3 space. They're all on the boundary. Every point on that circle belongs to the closure of any orbit of a point inside. So that's why it's called the limit set. These are the limit points of any orbit of an interior point. All right, so groups of this kind are called Fuchsian groups. Fuchs having been the person that first thought about them. And when you take the quotient, at least in a cartoon picture, you get a manifold which is diffeomorphic to the product of a compact surface with R. And if you like, it has a nice closure. You could think of it as having a closure which is which looks like a Riemann surface times the closed unit interval. Here, I'd like to choose a particular parameter along to represent the height here. The one that's convenient that plays a role for reasons I discovered later. I now call this the tunnel vision function, and it is characterized by the fact that it is harmonic, that its boundary value is 0 at the lower boundary and +1 at the upper boundary. And so you could, of course, write this down explicitly. For example, in the previous picture, there's a totally geodesic embedding of a genus of a compact surface, and you can look at the sign distance from that, and here's, in terms of that sign distance, where it's positive on one side, negative on the other. Here's what the formula actually looks like. But conceptually, you should think of it. This is the harmonic function on this hyperbolic manifold, which is 0 at one boundary component and 1 at the other. That's the Dirichlet way of constructing this. And the reason it's called the tunnel vision function, by me at least, is that at an interior point, what you can actually compute this by saying, I look out what fraction, I look at this boundary component, I look at that. Most of the geodesics coming to me actually start at one side or the other. Paint this side black, paint that side white. What fraction of the sphere is coming from that end of the tunnel? Okay. So it turns out that is a procedure for generating a certain harmonic function. It's one with this Dirichlet data. All right, so from this you can construct a scalar flat Kaehler manifold. You choose k points in this hyperbolic 3 manifold, and we want to play the same game before. But we're eventually going to have satisfy a quantization condition, which is not trivial in this case. So the extra condition is you require that the sum of the tunnel vision functions at those k points, that they add up to an integer. So for example, it's easy to make, if you only have one point, you can't do it. But if you have at least 2, you could certainly find 2 points where the values of this function add up to 1. And in fact, you can do this if you, just as long as you have at least either 0 points or 2 or more points. All right, so now the game is you take the Green's functions of these points. So you could, abstractly, this is saying that the positive Laplacian applied to the Green's function is 2 pi times the delta function. And where the Green's function goes to 0 at infinity, you can write these down explicitly in terms of infinite sums of the kinds of you could pass the universal cover and take over the pre-images of the point in the universal cover, add up the Green's functions in hyperbolic space. That's the way I did it in the original paper, and it may not be so easy to read for that reason. Anyway, you do the same thing as before. Take 1 plus the sum of the Green's functions. That's a harmonic function. Now you'd like to say, let's think of star dV as the curvature of a circle bundle. Well, that condition about the position of the points with respect to the tunnel vision function is exactly saying that the homology class is an integer class. You still have little spheres around these points. There's no problem coming from those. The problem is that you have a surface which is essentially at this place at infinity. And getting the integral on that turns out to be computable in terms of it's essentially the tunnel vision function of the given point. Now you add them up. You arrange that gives an integer. All right, so so now one goes through. So there's a particular conformal factor again. Now we want to take VH plus V inverse theta squared with a specific conformal factor that is f times 1 minus f. So that's a function which vanishes at both ends. And then what happens is that when we take the Riemannian completion of this metric, it's actually a compact, smooth, compact, complex manifold. And we have constructed on the Kaehler metric with scalar curvature identically 0. So the way the Riemannian completion actually happens is that we have this circle bundle over the punctured 3-manifold. We put in 1 point for each of the punctures, and we also put in copies of the boundary surfaces. So it turns out it's not obvious when you take the completion of a Riemannian manifold as a metric space. Usually it's not a smooth manifold, but in this case it is. And that involves detailed local calculations. And it turns out that in fact what we've created in this case is diffeomorphic to the original surface times S2 connected sum with KCP2 bars. And moreover, it's actually literally it's the blow up of if you take Riemann surface times CP times a certain CP1 bundle, and you now so the generic if this is the picture we think of the 3-manifold as the product of the Riemann surface times the open interval from 0 to 1, the inverse image of a general point. Oops, I'm sorry, I'm over time. So I should I have to bring this to a close. Anyway, you can actually figure out that the blow-ups are actually two spheres that join one of these puncture points to a boundary component, with the pre-image of that in the circle bundle. All right, so to try to wrap things up quickly, this was a very good method for creating scalar flat Kaehler metrics, and later using some very explicitly twistorial techniques with Kim and Pontecorvo and Singer, we developed a good theory of scalar flat Kaehler surfaces, so complex dimension 2, Kaehler metrics with scalar curvature identically 0, that foreshadowed much more recent results on constant scalar curvature Kaehler metrics and more generally extremal Kaehler metrics in the sense of Calabi. On the other hand, most small anti-self-dual deformations of these manifolds are not scalar flat Kaehler anymore, but they turn out to still be, with the right conformal factor, they're still almost Kaehler. And you could ask the question about large deformations. So this was recently explored in my joint paper with Chris Bishop. So in Kaehler geometry, you have a symplectic form, an interval complex structure, and a metric related in a certain algebraic way. And to say it's almost Kaehler, you don't require that the almost complex structure is integrable anymore. You still have a symplectic structure. In dimension 4, that's a very simple picture because it's actually saying you have a Riemannian 4-manifold with an orientation and a self-dual harmonic 2 form whose length is identically 1. Since if you're looking at an anti-self-dual, since we're asking this question about conformal classes, up to conformal rescaling, you're just asking your metric has a harmonic self-dual 2 form which doesn't vanish anywhere. Because then if it doesn't vanish anywhere, you can conformally rescale, so it has constant length. And this is then turns out to be an open condition in the C2 topology. So when I said before, if you were to perturb any of the things we wrote down, it would be actually could be thought of in almost-Kaehler terms. Now the cool thing that now takes over is the so-called, that makes it possible to push the previous story much further, is the simultaneous uniformization theorem of Bayer's from 1960. So using quasi-conformal mappings, he proved this amazing thing. So if you have two compact Riemann surfaces of the same genus, and you choose an isotopy class of diffeomorphisms from one to the other, then you actually can construct a hyperbolic three-manifold, which is essentially unique, which has those two Riemann surfaces as the boundaries. So that's called a quasi-Fuchsian three-manifold, and the group action that's associated with it is called a quasi-Fuchsian group. So in the previous condition, previous version, we were just taking an action in hyperbolic 2 space and extending it to hyperbolic 3 space. But what you can do is take the generators of that group and perturb them in some crazy way, still with the same relation on them. And what will happen is that the limit set, instead of being a nice circle, as in the Fuchsian case, becomes a so-called, what's a Jordan curve of Hausdorff dimension greater than 1. So this is still a topological embedding of the circle, but it's very, very non-smooth, and in fact its image has Hausdorff dimension bigger than 1. So that's the quasi-Fuchsian picture. And what comes out of it is that rather than thinking about just this hyperbolic three-manifold that had two copies of the same Riemann surface as at the boundaries, you can actually choose any two Riemann surfaces of the same genus and put them at infinity. And now you can repeat exactly the same story, and everything I've told you works. In particular, I mean, so here the way I described this special function, the tunnel vision function, it's harmonic, it's 0 at one end, it's 1 at one end. There's a unique such function. Okay, so you can now just imitate exactly the same story. It's the same story, it works exactly the same way. You get the same diffeomorphism type as before, but it's no longer a Kaehler metric. So when is this thing actually conformally almost Kaehler? The cute point is this happens if and only if the tunnel vision function has no critical points. And you can show that's an open condition on the group action. So the proof of that is that here I'm going to write down a harmonic self-dual two-form. All it has to be is it has a closed self-dual two-form that is regular on the manifold. So this is a manifold with b plus equal to 1. And there's only one such thing up to scale. So I just have to write down an example. I take d of the tunnel vision function, wedge the connection 1 form, take this potential v times star of df, and you can check that that is now a closed. So you can actually write down the harmonic 2 form. If f has a critical point, this has a 0. You might worry, well, there's a little bit of delicacy at infinity, puncture points. It's obvious, though, that if it has a critical point at a kind of a generic interior point, you're going to be in trouble. In fact, you can check that that's exactly the full answer. So what comes out of this? Now you just have to produce some examples that have very bad tunnel vision functions. That's what Chris Bishop and I did. So, so the statement is if you fix an integer k greater than or equal to 2, you take a Riemann surface of genus at least 2 and look at this connected sum, then you can find a family of anti-self-dual conformal classes on it, where initially you start at a scalar flat Kaehler metric, and finally you end up with a Kaehler class that is not represented by an almost-Kaehler metric. In other words, its self-dual harmonic 2 form has to have a 0 somewhere. Okay, and I'm out of time, so I'm going to just wrap up very quickly to say that the idea depends on the theory of quasi-conformal mapping of CP1, going back to Alfors and Bayer's. And the idea is you take some curve in the plane, which just looks called a dog bone. It has, you have a couple of circles joined by a corridor, and trying to understand, well, if this limit set was exactly 2 circles, well, certainly you have a function. This tunnel vision function would certainly have a critical point. That persists if you put in a small corridor. And then what you end up doing is use quasi-conformal mapping to approximate this curve by another curve, small, very close to it in Hausdorff distance, which is actually the limit set of a group action. Okay, so that's the way the story goes. There are various questions would have liked to ask, but I'm kind of out of time, so I will not really be able to talk about things like almost-Fuchsian manifolds and hyper-Kaehler metrics on the moduli space of quasi-Fuchsian manifolds. Instead, I'll just thank the organizers for the invitation, and it's a real pleasure to be here, and I got the scaling wrong, so you can't see much of my picture of Cambridge. Okay, so thanks a lot. Thank you for your attention.
Questions?
So you have these scalar flat Kaehler metrics on blow-ups of ruled surfaces with at least k blow-up points, for at least 2 blow-up points. What about for blowing up at 1 point?
All right, so the metrics I've been describing, this earliest construction produces metrics that have a circle action. And certainly that's not typical for most scalar flat Kaehler metrics. So in order to get further, what we actually had to do was step out of this kind of concrete construction and construct suitable twistor spaces with divisors. And it's a generalization of the Donaldson-Friedman gluing theorem for getting connected sums. So what we were able to do was eventually to get, so the 1-point blow-ups do exist, but you don't get them in this easy way. But also, the examples I was describing have large fundamental groups. It's much harder to construct examples that are simply connected, but they do exist. And if you're interested, our paper appeared in Krella, maybe 94, somewhere around there.
Okay, maybe since we're a little over time, if you have any other additional questions, please talk to Claude, and let's thank him for the beautiful lecture.